Hello, students. The last topic we have studied about the electrostatic potential. Electrostatic potential at a point is the amount of work done in bringing the charge from infinity to that point in an electrostatic field due to charge configuration without acceleration. The formula for electrostatic potential difference is WAB upon Q equal to VB minus VA, means work done per unit charge. Now if we have to write the potential difference between 2 points A and B, and we are moving charge from A to B, then work done per unit charge is equal to VV minus VA. VV minus VA is the potential difference between 2 points A and B. Now unit for electrostatic potential difference is 1 volt. It is a scalar quantity. If we have to define 1 volt, then it can be defined as it is the amount of work done in moving a unit positive charge from one point to other against the electrostatic force of the field without acceleration. Or electrostatic potential difference between 2 points in an electrostatic field is set to 1 volt when 1 joule of work is done in moving a positive charge of 1 coulomb from one point to other against the electrostatic force of the field without acceleration. Now the electrostatic force or electrostatic field is a conservative field. We have to prove it. We know that conservative field is that field in which work done by or against the field or against the force depends only upon initial and final position. It does not depend upon path. Or we can say that electrostatic field will be a conservative field if work done in moving a unit positive charge around a closed path is always 0. So we will prove that the total work done around a closed path is equal to 0. When we move a charge from point A to B along the path L and then bring it back from B to A along the path L dash in a electrostatic field. There will be electric field in this space, and we are moving the charge in that field from A to B, then B to A. So work done from A to B along path L will be equal to WAB upon Q naught, work done per unit charge equal to BB minus B. We are moving charge from A to B, so we have to write here BB minus B. That would be equation number 1. If we bring back the charge from B to A along path L dash, then work done from B to A, work done per unit charge is equal to BA minus BB. That will be equation number 2. Now total work done. Total work done in carrying a unit positive charge over the closed path A to B, then B to A. We will add equation number 1 and 2. WAB upon Q naught plus WBA upon Q naught equal to WAB to A upon Q naught equal to BB minus VA plus VA minus BB. So these will cancel out and we will get work done from A to B to A equal to 0. So our total work done from A to B to A equal to 0. This shows that the electrostatic field is a conservative field because the work done around a closed path, work done in moving a unit positive charge around a closed path in an electrostatic field is come out to be 0. Now we can write, we know that v dw is equal to f dot dl, and this is our small work done. If we have to find total work done, we will integrate it, equal to integration of f dot dl. This is equal to 0. Now if we are taking a unit positive charge, then F will be equal to QE. Here Q is 1. 1 into E. So F will be equal to E for unit positive charge. So we can write this equation as, in place of F, we will write E. So this equation can be written as closed integral of E dot dl equal to 0. Since our path is closed, so we draw a circle over integration, and this is pronounced as closed integration around a closed path. Integration around a closed path. So for electrostatic field, E dot dl equal to 0. Closed integral of E dot dl equal to 0. Now next topic is electrostatic potential due to a point charge. We have to find the potential due to a positive charge Q. Suppose that there is a charge plus Q at point O. If we have to find the electrostatic potential at point P at a distance r from charge plus Q, then according to definition, electrostatic potential due to a charge is the amount of work done in bringing the charge from infinity to that point. So we will place a unit positive charge at infinity. If we bring this unit positive charge from infinity to point P, then that will be equal to our potential at that point. So first we calculate the work done for a small displacement dx from A to B. So at point A, there will be electric field due to charge plus Q, and that electric field will be along this direction, because this plus 1 coulomb charge will experience a force along this direction, so electric field will also be along this direction. So small amount of work done in bringing the charge, unit positive charge, from A to B is equal to dW is equal to ED E dot dx. Since we are considering here unit positive charge, so you have to write here E, because F equal to E. And the angle between E and dx, E is along this direction and dx is along this direction, so angle is 180 degree. So cos 180 is minus E minus 1, so it will become minus E dx. Now total work done. If we have to find total work done in bringing the charge from infinity to point R, then we will integrate it. So dW is equal to minus E dx. So when we have to find total work done, then we will integrate it on both sides from infinity to point R. So this will be the total work done. When we put the value of E equal to Q upon 4 pi epsilon naught x square dx, then we will get Q upon 4 pi epsilon naught. This term is constant, it is taken out of integration infinity to R x minus 2 dx. Now integration of infinity to R x minus 2 dx. This is equal to x raised to power minus 2 plus 1 upon minus 2 plus 1 infinity to r. This will be equal to minus 1 by x infinity to r, and this is equal to minus 1 by r minus 1 by infinity. So this will become 0, and this is equal to here we have to write minus. Now x raised to power minus 2 integration of x to power minus 2 dx, this is equal to minus 1 by r. Now when we put the value of this integration over here, then we will get this minus and this minus becomes plus. So here the potential will come out to be positive. So when you put the value of this over here, you will get plus, potential to be positive. So due to a positive charge, the potential will come out to be positive. If r equal to infinity, then this potential becomes 0, means at a very large distance from the charge, the potential will come out to be 0. Now if we plot a graph between electrostatic potential and distance r when charge is positive, then we know that V is inversely proportional to R and E is inversely proportional to R square. So graph will come out to be like this. For electric field shown by dark line, for potential shown by dotted lines. Now when charge is negative, the variation of V with R, potential with R is shown here. The electric potential will be negative for negative charge, so it is taken along negative y-axis and distance along positive axis. So graph will come out to be like this. Now if we plot a graph between V and 1 by R, since V is inversely proportional to 1 by R, inversely proportional to R and directly proportional to 1 by R. So V is directly proportional to 1 by R, so graph will be a straight line if charge is positive. And if charge is negative, then potential will be negative, taken along negative y-axis and 1 by R along x-axis. Then again it will be a straight line because V is directly proportional to 1 by R.